Welcome to classical mechanics course. Today we will try to see the oscillations, simple harmonic motion, and damped oscillation, undamped and damped oscillations, also driven oscillations. Simple harmonic motion is a kind of motion which is very widespread in daily life. But the basic model for such motion can be given by the mass spring system. For example, we may have a mass, a block attached to the block of mass M attached to a spring of force constant K, and this is the equilibrium position. Assume there is no friction between the surface and the object. If you elongate it from the equilibrium position by some distance x, then of course it requires some force to pull it to one side. This is your force, because you have to apply a force to pull it, and then immediately you feel the restoring force of the spring which tries to take it back. And the equation of motion for such kinds of motion is mx double dot. Remember, x double dot means the second time derivative, because we know that x dot is dx by dt, first time derivative. X double dot is d squared x by dt squared. So m times x double dot, which is the Newton's second law, F equals ma type of equation. Here we have m times a. But what is the force on this object when you leave it? It is just a restoring force. Since it is backward, x is positive to the right, but restoring force is trying to pull it back. It's a negative force, k times x. Hooke's law. Force is displacement proportional to the displacement, and vice versa. So we can take it back. So x double dot m times x double dot plus k times x is a 0, and if you divide by m, you get the equation of motion. And this is the equation of motion for such a system. Which kind of solutions can we have for such equations? Of course, x should be a function such that when added, when first multiplied by this constant and added to the second time derivative, should be a 0. And the only forces, the only choices are a sine or a cosine. So x can be, let me write the x of t because it's a function of time, an amplitude cosine omega 0 t minus delta, or another, again an amplitude, but a sine function, omega 0 t minus another phase phi. So either one can be used, because both a cosine and a sine, when taking the second derivative, gives us also a cosine or a sine, so that when you add them, we may get a 0, provided that this omega 0 is the term k over m. So omega 0 squared is k over m. Because when you take, for instance, let us choose the first one. If x is a cosine function, then x dot, first time derivative, will be amplitude a. Omega 0 will come from the inside. Omega 0, cosine will be minus sine. Omega 0 t minus delta. Delta is the phase which is not very important in such analyses. But let's take x double dot. We have a minus sign and a, but now another omega 0 will come from the inside. Argument of the sine function. Sine becomes now cosine omega 0 t minus delta. So when you rewrite this equation, so x double dot is this. Let me write the x double dot term first. Minus a omega 0 squared and cosine omega 0 t minus delta. Next we have K over M, but X was chosen by us as the first one, A cosine omega 0 t minus delta is 0. So we can cancel, eliminate the cosine terms, because the right hand side is already 0. You can also divide by A, so omega 0 squared turns out to be K over M, and therefore this natural frequency is the root of K over M. Omega 0, I insist to write on with this omega the index 0, because it is not just an omega. In such calculations, omegas are generally used for the external oscillations, driven frequency of driven oscillations. However, if you write this 0 as the index, this is the natural frequency of the oscillations. For instance, this may be a vertical case. Okay, you may hang a block at the end of this spring of force constant K mass M, and if you take it a bit down or a bit up, then these will make oscillations, and frequency of these oscillations is omega 0. It depends on how stiff the spring is and how heavy the mass is. Omega 0 is root K over M. All right. Now let us consider further some more complicated cases. Let's consider, this is the undamped case, and this is called undamped. Undamped cases are not very realistic, because in nature there is always some kind of friction or other kinds of resistive forces. Resistive forces. But this is very ideal. This is the case. Very ideal. In reality, we don't have such ideal cases, because anyway, even if the friction in on this table is very negligible, sooner or later this system will stop to oscillate and will come to rest at the equilibrium position. So this is not very realistic. Maybe for some little amount of time they can be taken as valid. However, in more realistic cases, we have to consider the damped oscillations. Damped means the oscillations will be, amplitude of the oscillations will be smaller and smaller, and at the end it will stop. Or there are other kinds of oscillations, as we will see. Now let's see damped oscillations. Okay? Damped, sönümlü. So sooner or later, eventually, the system will cease to oscillate, to vibrate. Now let me consider now the resistive force. There may be a resistive force. But let's not think about this resistive force as a friction, because frictions are generally constant forces. Because friction is depends on two factors. One is the coefficient of friction between these two surfaces, and the normal force, again, applied by the surface on the object. However, resistive here means it is, let me call it Fr, resistive force, or F-res, resistive force, is proportional to the velocity. How fast the object is moving. The greater the velocity, the greater will be the resistive force. But velocity, we don't write it as v in this analysis, we write it as x dot, remember. X dot is velocity. X double dot is acceleration. X is position. So F is proportional to x dot. Now let's see the new form of the equation, because m times x double dot was previously k times x because of the restoring force. Now we have, let me draw the picture again. This is the object, and for instance, that's the equilibrium position. We have pulled it to the right hand side, and there is the force, restoring force Fr and resistive force also. Both are trying to work against it. So both are now have to be written as negative terms. Minus Kx minus B times x top. So there are two terms on the right hand side which are both negative. So let's take them to the left hand side. Mx double dot plus B times x dot plus K times x is equal to 0. Now in addition to the previous form of the equation, we also have this middle term, which is the resistive force. It depends on how fast the object is moving at that moment of time. And B is a positive coefficient. Divide by m so that the first term we have 1 as the coefficient. So the new form is x double dot is B over m x dot plus K over m x. The right hand side is again 0. Now let's write this second last part. We know that it is omega 0 squared. There is nothing new here. But what about the middle term? Let us define a damping parameter. Let us define a damping parameter. Damping means how soon, how fast the system will lose the oscillations. The greater the damping, the shorter the time to reach the equilibrium. What is that parameter? Let me call it beta. Beta is defined as B over 2m. Why do we choose such a definition? We will see, to make the calculations easy. So beta is let us define a damping parameter. This is beta. And beta is defined as this coefficient B over 2m. So what do we have here? We have B over m. We have the coefficient of the term B over m. But B over m is just 2 beta. B over m can be written as 2 beta. So let me write the equation in the final form. X double dot plus 2 beta times x dot plus omega 0 squared times x, it is equal to 0. What do we see here? It is a second order linear constant coefficient differential equation. It is second order because the first one is second derivative, linear because there is no square, constant coefficient because 2 beta and omega 0 square are just constants, and it's a relatively simple differential equation. Now let's see the possible solutions for this equation.